Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on the periodic table. So let's go ahead and get started with problem number 1. Problem number 1 says lithium and sodium have similar chemical properties. For example, both can form ionic bonds with chloride. Which of the following best explains this similarity? Now, lithium and sodium are both elements that are found right here on the periodic table. Now, we know from our discussion that the periodic table is organized in such a way that elements with similar properties are grouped together. And one key aspect to consider is the concept of groups and periods. Now, groups are the vertical columns in the periodic table, and elements in the same group often exhibit similar chemical properties because they have the same number of electrons in their outermost shell. Periods, on the other hand, are the horizontal rows, and elements in the same period, they don't necessarily have similar chemical properties. Now, given this background, let's go ahead and begin to explore each of our options. Now, option A says both lithium and sodium are positively charged. Now, while this is true that both lithium and sodium form positively charged ions, this fact alone does not explain why they have similar chemical properties. The positive charge is a result of losing one electron, but it doesn't really account for the broader similarities in their chemical behavior. Then option B says that lithium and sodium are in the same group of the periodic table. Now, this is a very promising answer. This is a correct answer because both lithium and sodium are in group 1 on the periodic table, also known as the alkali metals. Elements in this group, they have one electron in their outermost shell, which they readily lose to form positive ions with a +1 charge. And this similar electronic configuration is what gives them similar chemical properties, such as their reactivity with chlorine to form ionic compounds like lithium chloride and sodium chloride. Now, if we look at option C says lithium and sodium are in the same period of the periodic table. Now, this is completely incorrect because lithium is in period 2 and sodium is in period 3. So they are not in the same period. In addition, elements in the same period do not necessarily share similar chemical properties. Instead, they exhibit trends across a period, like increasing electronegativity or atomic size, etc. All right, then our last option here says both lithium and sodium have low atomic weights. Now, while lithium and sodium do have relatively low atomic weights compared to many other elements, this characteristic does not directly explain their similar chemical properties. The atomic weight affects physical properties more than it does chemical reactivity. And so, all in all, the correct answer here is going to be answer choice B. Lithium and sodium are in the same group of the periodic table, hence why they have similar chemical properties. Now, let's move on to problem 2. Problem 2 says carbon and silicon are the basis of biological life and synthetic computing, respectively. While these elements share many chemical properties, which of the following best describes a difference between the two elements? Now, carbon and silicon are right here. They are in the same group. They're located in group 14. Now, carbon is located in group 14, period 2, while silicon is in the same group, group 14, but it's in period 3. Now, being in the same group means that they share some chemical properties, such as having the same number of valence electrons. However, being in different periods indicates differences in their physical properties. Something like atomic radius would be different here based off of a comparison of their periods. Now, the atomic radius, this is important. This is the distance from the center of the atom's nucleus to the outermost shell of electrons. And as you move down a group in the periodic table, the atomic radius increases because additional electron shells are added. In lecture, we said it in reverse. All right, we said going from bottom to top, all right, going from bottom to top, atomic radius decreases. You can say it in the opposite way as well. Going from top to bottom, atomic radius increases, whichever sticks better. Now, with that point in mind, that means that silicon in period 3 is going to have a larger atomic radius compared to carbon. So if we're comparing atomic radius, silicon is going to have a larger atomic radius than carbon. Let's keep that in mind as we analyze each option that's provided in this question. A says carbon has a smaller atomic radius than silicon. This is a true statement. The statement is accurate. As we mentioned, carbon is in period 2, silicon is in period 3, so carbon's atomic radius is smaller due to having fewer electron shells. Now, option B says silicon has a smaller atomic radius than carbon. This is incorrect for the reasons that we just explained. All right, it will have more electron shells, so it will actually have a larger atomic radius than carbon. Option C says carbon has fewer valence electrons than silicon. Now, this is incorrect because both elements have 4 valence electrons. They're in the same group, group 14, which means that they share the same number of valence electrons. Both elements have 4 valence electrons. All right. Keeping that in mind, let's go on to answer choice D. It's kind of related to C here. It says silicon has fewer valence electrons than carbon. Again, incorrect. For the same reason, both elements have 4 valence electrons. So now that we've worked through the options, the only option that seemed reasonable and is correct is answer choice A. All right. Which of the following best describes a difference between the two elements? Carbon has a smaller atomic radius. Wonderful. Let's move on to problem 3. Problem 3 says, which of the following elements has the highest electronegativity? Is it magnesium, chlorine, zinc, or iodine? Let's review what electronegativity means. Electronegativity is a measure of an atom's ability to attract and retain shared electrons in a chemical bond. Electronegativity is influenced by an element's atomic number and the distance that its valence electrons reside from the nucleus. Higher atomic numbers and shorter distances between the nucleus and valence electrons results in higher electronegativity. Now, what are the trends for electronegativity? Let's scroll down here and review what we discussed in lecture. Going from left to right on the periodic table, electronegativity increases. Electronegativity increases due to the greater effective nuclear charge, which allows atoms to attract bonding electrons more strongly. What about going from bottom to top? What's the trend for electronegativity? It increases as well because atoms higher up in a group have fewer electron shells, resulting in a stronger attraction between the nucleus and the valence electrons. So taking that all into consideration, let's figure out where all of the option choices, where we can find them on the periodic table. So magnesium is right here. Magnesium is located in group 2. It's an alkaline earth metal, and it's in period 3. All right, magnesium is going to have a relatively low electronegativity because it is more metallic, and it's located here on the left side of the periodic table. All right, and we said that our trend for electronegativity increases as you go more right. All right, so we're going to keep that in mind as well. Then we have zinc. Zinc is located here in group 12 and period 4. 4, and it is a transition metal. And transition metals typically have moderate electronegativity, but we want to compare it to some of the other answer choices, keeping in mind our two trends, all right, going from left to right and bottom to top. Then we have chlorine and iodine. These are both halogens, so they're located here in group 17. Here's chlorine, here's iodine. All right, now halogens, this is really important. Remember that halogens are highly electronegative due to their strong desire to gain just one more electron and achieve a noble gas configuration. And keeping in mind our trend going from left to right increases electronegativity, chlorine and iodine are the furthest right here. So we're going to go ahead and cancel out zinc and magnesium as answer choices and really focus in on chlorine versus iodine. Now, they're both further right. They're in the same group. So now we have to fall back on our second trend for electronegativity, the one that tells us that going from bottom to top increases electronegativity, which means that chlorine stands out as the most electronegative. And so the correct answer here for 3 is going to be B. Wonderful. Let's move on to problem 4. Problem 4 says ionization energy contributes to an atom's chemical reactivity. Which of the following shows an accurate ranking of ionization energies from lowest to highest? And if you look at the answer choices, the 3 things that we have to rank are the first ionization energy for lithium, the first ionization energy for beryllium, and the second ionization energy for beryllium. So these are the 3 things that we're trying to rank from lowest to highest ionization energy. So in this question, we obviously need to understand the concept of ionization energy to determine the correct ranking of ionization energies from lowest to highest for lithium and beryllium. Now, ionization energy, this is the energy that's required to remove an electron from an atom in the gas phase. The first ionization energy refers to removing the first electron. The second ionization energy refers to removing the second electron, and so forth. Now, generally, ionization energy, we said, increases going from left to right, and ionization energy increases going from bottom to top. So these are important trends to remember. So then examining the 3 things that we need to rank, first ionization energy of lithium and first ionization energy of beryllium and second ionization energy of beryllium, let's start to think about this, all right? Lithium is right here, all right? It is in group 1, period 2, while beryllium is in group 2, period 2. Now, the first ionization energy of an element is really influenced by the effective nuclear charge. This is the net positive charge that's experienced by that electron in the outer shell. And it's also influenced by the distance of the electron from the nucleus. Now, for lithium, with only one electron in its outer shell, that first ionization energy is relatively low because it will readily lose this electron to achieve a stable noble gas configuration. So like we said, lithium has that one electron in its outermost shell, whereas beryllium would have 2. And removing an electron for lithium in its outermost shell is going to be easier than to remove the electron from beryllium. For beryllium, with 2 electrons in its outer shell, that first ionization energy is going to be higher because it's slightly more challenging to remove an electron from a more stable configuration. And so comparing just the first ionization energy of lithium and the first ionization energy of beryllium, that first ionization energy of beryllium is going to be higher than the first ionization energy of lithium. So the relationship between these two is going to be that for beryllium, it's going to be higher. Now, The second ionization energy is the energy that's required to remove a second electron after that first has been removed. And this is typically much higher than the first ionization energy because removing an electron from a positively charged ion is more difficult due to that increased electrostatic interaction, attraction, I should say, between the nucleus and the remaining electrons. And so the one that's going to have the highest ionization energy is that second ionization energy for beryllium. And so our ranking going from lowest to highest is going to be first ionization energy of lithium, followed by first ionization energy of beryllium, followed by second ionization energy of beryllium. And that's going to relate to answer choice C. So 4 is C. Fantastic. Let's move on to problem 5. Problem 5 says antimony is used in some antiparasitic medications. What type of element is antimony? Now, elements in the periodic table are categorized into metals, metalloids, and nonmetals based on their physical and chemical properties. Metals are typically characterized by their ability to conduct electricity and heat, their malleability, and their ductility. Nonmetals, on the other hand, are the opposite of metals. They're poor conductors of heat and electricity, and they're also not very malleable or ductile. Metalloids, they have properties that are intermediate between metals and nonmetals, and they often exhibit characteristics of both. Now, antimony is right here on the periodic table. It's in group 15 of the periodic table. Now, when we talked about metalloids, we said that they lie somewhere around this stair step that we drew out here. And we said metalloids are going to be the elements that are near this stair step that we drew in our periodic table. Antimony falls on this stair step, and it actually exhibits a combination of both metallic and non-metallic properties, making it a metalloid. So antimony is going to be a metalloid, making the correct answer for 5 B. Let's move on to problem 6. Problem 6 says the properties of atoms can be predicted to some extent by their location within the periodic table. Which property or properties increase in the direction of the arrows shown? Electronegativity, atomic radius, and first ionization energy. So let's review these 3 properties first. Electronegativity. This is the ability of an atom to attract electrons towards itself in a chemical bond. Now, reviewing our trends, we said that electronegativity increases going from left to right, and it increases going from bottom to top. So electronegativity follows the trends that are shown right here. Then we discussed atomic radius. This is the distance from the nucleus of an atom to the outermost electrons. The trend for atomic radius is that it decreases going from left to right. Atomic radius actually decreases. All right, so it doesn't follow this first trend. In addition, it also decreases going from bottom to top. So atomic radius does not follow the trend that is shown here. All right, we're looking for properties that increase in the direction of the arrows shown, and atomic radius does not. Electronegativity does, however. All right, what about ionization energy? First ionization energy. This is the energy that's required to remove the outermost electron from an atom in the gas phase. And the trends that we went over for ionization energy is, in fact, that it increases going from left to right, and it increases going from bottom to top. So it follows the trends that are shown in the arrows here. So electronegativity and ionization energy are properties that increase in the direction of the arrows that are shown, making the correct answer for 6C. Beautiful. Let's do problem 7 now. Problem 7 reads, metals are often used for making wires that conduct electricity. Which of the following properties of metals explains why? A says metals are malleable. B says metals have low electronegativities. C says metals have valence electrons that can move freely. And D says metals have high melting points. Now, metals are known for their characteristic physical and chemical properties, including malleability, ductility, conductivity, and luster. But one of the most critical properties that's related to electrical conductivity is the presence of free-moving valence electrons. These valence electrons are not tightly bound to any particular atom, and so they can move freely throughout the metal lattice. And this movement of electrons is what allows metals to conduct electricity efficiently. So while these answer choices are correct, all 4 descriptions of metals are true, we're trying to look for the answer choice that most explains the properties of metals that contribute to their ability to conduct electricity, and that's going to be answer choice C. Metals have valence electrons that can move freely. Now, moving on to problem 8. Problem 8 says, which of the following is an important property of the group of elements shaded in the periodic table below? Wonderful. Now, in this problem, we're asked to identify an important property of the group of elements that's shaded. The shaded elements belong to group 2, which consists of alkaline earth metals. These elements include beryllium, magnesium, calcium, strontium, barium, and radium. So let's analyze the options and work through the problem that way. So answer choice A says these elements are the best electrical conductors in the periodic table. While alkaline earth metals do in fact conduct electricity, they are not the best conductors. The best electrical conductors are actually found in group 11. They include copper, silver, and gold. So that's an important thing to keep in mind. All right, they're not even as effective as the alkali metals. So with that being said, we can go ahead and eliminate answer choice A. Answer choice B says these elements form divalent cations. This is a correct statement. Alkaline earth metals, typically they lose 2 electrons to form +2 ions, so divalent cations. So for example, magnesium tends to lose 2 electrons to form magnesium 2+. Same goes for calcium. It loses 2 electrons to form calcium 2+. So this property is a key characteristic of group 2 elements. So we're going to keep option B here. We're not going to eliminate it, but we still want to go through the rest of the options. Option C says the second ionization energy for these elements is lower than the first ionization energy. This statement is incorrect. From lecture, we made a clear distinction that the second ionization energy is always higher than the first ionization energy because removing an electron from a positively charged ion is going to require more energy due to the increased electrostatic attraction between the nucleus and the remaining electrons. So option C is totally incorrect. We're going to go ahead and eliminate. Then answer choice D says that the atomic radii of these elements decreases as one moves down the column. This is also incorrect because the atomic radius actually increases as you move down a group in the periodic table. Now, when we learned the trend for atomic radii, what we said is that going from bottom to top, atomic radius decreases. All right. That means the opposite is also true. Going from top to bottom, the atomic radius increases. This statement is incorrect then, all right? The atomic radius actually increases as you move down a group in the periodic table, and this increase is due to the addition of electron shells, which places the outermost electrons farther from the nucleus. So that means we can also eliminate answer choice D. The only correct answer here is going to be Answer choice B. These elements form divalent cations, and this property accurately describes the behavior of the alkaline earth metals in group 2 because they typically lose 2 electrons to form cations with a +2 charge. Now we can transition into problem 9. Problem 9 asks, when dissolved in water, which of the following ions is most likely to form a complex ion with water? We have sodium ion, iron 2 ion, chloride ion, and sulfide ion as our options. Now, to answer this, we need to understand the concept of complex ion formation. A complex ion consists of a central metal ion that's bonded to one or more molecules or ions via coordinate covalent bonds. Now, water molecules, they can act as ligands due to their lone pairs of electrons on that oxygen atom, which can then coordinate to a metal ion. And typically, transition metal ions are more likely to form complex ions with water because they have a high charge density and they can accept electron pairs from ligands. Now, in other words, transition metals, they can form more than one ion, and so the transition metals in these various oxidation states can often form hydration complexes with water. And part of the significance of these complexes is that when a transition metal can form a complex, its solubility within the related solvent is going to increase. Now, the only transition metal option we have here is the iron 2 ion, and that is going to be the correct answer here for problem 9. It's going to be B. The other ions that are listed here, they might dissolve readily in water, but because none of them are transition metals, they will not likely form complexes. Now let's move on to problem 10. Problem 10 says how many valence electrons are present in elements in the third period. So this right here is the third period, and this question is actually really easy if you recall that period refers to the rows in the periodic table, while groups refer to the columns on the periodic table. Now, within the same period, what we know is that an additional electron is added with each step towards the right side of the table. And so, how many valence electrons are present in elements in the third period? The number increases as the atomic number increases. And so the correct answer here for 10 is D. If you happen to switch the definitions for periods and for groups, you might have accidentally chosen answer choice B. But if you remember the definitions, then this would be a really easy problem to get. So 10 is D. Let's move on to example 11. Problem 11 says arsenic mediates some of its toxic effects via the inhibition of acetyl-CoA formation and the inhibition of the enzyme succinic dehydrogenase to decrease AT production. In addition to its metabolic effects, arsenic can also replace phosphorus in many reactions. Which of the following best explains the similarity between these two elements? Is it similar atomic numbers, similar number of electrons, or similar valence configuration? Now, arsenic and phosphorus are right here on the periodic table. They're both located in group 15 of the periodic table. Now, elements in the same group, they have similar chemical properties because they have the same number of valence electrons. The valence electrons determine how an element interacts chemically, including the types of bonds it can form and its reactivity. So let's evaluate each of these options. Answer choice A says similar atomic numbers, and this is just incorrect. Atomic numbers are unique to each element, and they increase sequentially across the periodic table. Phosphorus has an atomic number of 15, while arsenic has an atomic number of 33. And although these elements have different atomic numbers, this just doesn't explain their similar chemical behavior. All right, and the answer choice says similar atomic number, which is just outright incorrect. Now, option B says they have a similar number of electrons. This is also incorrect. Now, both elements have different total number of electrons. 15 for phosphorus, 33 for arsenic. What they do have in common is the number of valence electrons, and that's what's crucial for chemical reactivity. All right, so this option obviously does not address the key aspect of their similarity, and it's actually just a outright incorrect statement. So we're going to go ahead and cancel answer choice B. Answer choice C says similar valence configuration. This is correct. Both phosphorus and arsenic have 5 valence electrons, and so they have a similar valence shell. They have the same number of valence electrons in their outer shell, and the similarity in their valence electron configuration leads to similar chemical properties, allowing arsenic to substitute for phosphorus in many biochemical reactions. They both have similar electron configurations. Phosphorus has near the ending 3s2, 3p3, and arsenic has an electron configuration of 4s2, 4p3 there. And that similarity in their valence electron configuration, where they have n numbers of s2 and n numbers of p3, that leads to similar chemical properties. And again, this explains why arsenic can interfere with biochemical processes that typically involve phosphorus. So with that, the correct answer for 11 is going to be C. Moving on to problem 12, this one says of the 4 atoms depicted here, which has the highest electron affinity? Now, electron affinity is the amount of energy that's released when an atom in the gas phase accepts an electron. Generally, elements with high electron affinity are those that can gain an electron to achieve a stable electron configuration, usually a complete outer shell. Now, to analyze this, we need to consider the electronic configuration and the positions of these elements in the periodic table. So atoms with nearly full outer shells, like the halogens, they tend to have high electron affinity because they release a significant amount of energy when they gain an electron to complete their valence shell. So let's examine each of these options. Answer choice A has a total of 8 electrons in its outer shell. It already has a satisfied octet. And so here, this element is not going to have the highest electron affinity because it already has a complete outer shell. If we look at answer choice B, there are 7 electrons in its outer shell. All right, this is very similar to the halogens, where they tend to have or tend to need only one more electron to complete their valence shell. So this element has the possibility of having a high electron affinity. Then if we look at C, there are 2 electrons in the outer shell. And if we look at D again, all right, this one also has 7 electrons in its outer shell. Now for answer choice B, we have 2 shells, and for answer choice D, we have 3. Now just looking at these possible answer choices, we can immediately eliminate A because it has a full octet. It doesn't want an additional electron. We can eliminate C because compared to B and D, who both have 7 electrons in the outer shell, these kinds of atoms tend to have high electron affinity because they release a significant amount of energy when they gain that electron to complete their valence shell. And C can't compete with B and D here. All right, so then focusing in on answer choice B and D. All right, B kind of resembles fluorine here, and D resembles chlorine. All right, and now here, fluorine and chlorine, they have the same valence electron configuration, and they have a similar amount of effective nuclear charge. How do we work through this? Well, we work through this because although they have similar valence electron configuration and amount of effective nuclear charge, when an electron is added to fluorine's valence shell, that negative charge is added to the second energy shell, which is quite small in physical size, And that means that the new electron is crowded into a small energy shell with 7 other electrons. And the result of adding an electron here to fluorine is the following. The energy is still released when an electron is added to fluorine, but not as much energy as might be predicted by the general trend alone. By contrast, though, if we add an electron to the chlorine atom here in answer choice D, all right, we're adding this new electron to the 3rd energy shell. And there is less repulsion among the valence electrons, leading to a slightly greater electron affinity for chlorine. And so the correct answer here is going to be D. All right, it's going to be chlorine. It has the highest electron affinity, and it's going to be the right answer. So 12 is going to be D. Let's move on to problem 13. Problem 13 asks, which of the following atoms or ions has the largest effective nuclear charge? So in this problem, we're asked to determine which of these given atoms or ions has the largest effective nuclear charge. And effective nuclear charge is the net positive charge that's experienced by an electron in a multi-electron atom. And it's calculated as the actual nuclear charge, Z, so like the number of protons, minus the shielding effect of the inner shell electrons, which we can write as S. All right, and so Z effect, all right, our effective nuclear charge is equal to Z minus S. Z is the atomic number, total number of protons. S is the shielding constant, so this is approximated by the number of core electrons. We can make that approximation here, it will hold. All right, so what we want to do then is evaluate each option and figure out the effective nuclear charge approximately for each ion. So our first option here is the chlorine atom. The atomic number for chlorine is 17, all right? And the electron configuration for chlorine is going to be, I'm going to write it out here, 1s2, 2s2, 2p6, 3s2, 3p5, all right? Now, the valence electrons, they're going to experience a shielding effect from the core electrons. The core electrons are going to be the ones that are less than the valence electrons. These are our valence electrons, the one in the greater principal quantum number here. All right. The valence electrons, the ones in the 3 shell, are going to experience a shielding effect from the core electrons, which are these electrons here. If we sum that up, that's 2 plus 2 plus 6. There are 10 core electrons. And so approximately here, the effective nuclear charge, we can think of it in a simple way, 17 minus 10. This gives us a value of 7. All right. Next, we want to work through chloride ion. So here, all right, the important thing to consider is that there is an extra electron here. Now, the atomic number stays the same, 17, all right? And now the electron configuration, it's not 1s2, 2s2, 2p6, 3s2, 3p5, but instead this 3p5 actually becomes 3p6. Okay, that still doesn't change the fact that we only have 10 core electrons. All right, that extra electron, it increases shielding slightly, but overall shielding is still primarily from those 10 core electrons. All right, and so our calculation is still 17 minus 10. All right, and that's going to be 7 here as well. Now, this is still important for us to note here, all right? We're going to keep in mind still, right? We're making this approximation calculation. Important to remember that the additional electron in the valence shell does mean it experiences slightly more repulsion compared to a neutral chlorine atom. So if need be, that fact alone could help us determine between answer choice A and B. But we still want to figure out C and D before we start to worry too much about ion versus neutral atom and comparing that. All right, so we're going to hold on to that fact for a little bit, but let's work through C. All right, C, we have potassium atom. Potassium atom has an atomic number of 19, and the electron configuration for potassium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. All right, potassium's right here. We're just reading it straight off of the periodic table. All right, we covered that in chapter 1. Now, the valence electrons experience a shielding effect from these core atoms right here. All right, so all the way up to 3p6. That's a total of 18 core electrons. All right, the valence electron experiences a shielding effect from 18 core electrons. So what we have now here for our effective nuclear charge calculation is 19 minus 18. So that gives us an effective nuclear charge of 1 for the potassium atom. All right, option D is potassium ion. Here it's a cation, so it loses an electron. Which electron does it lose? It's going to lose that 4s1 electron. So actually the electron configuration for potassium plus is just 1s2, 2s2, 2p6, 3s2, and 3p6. All right, so it still has the same atomic number, obviously 19, but now the number of core electrons is different. If this is just the electron configuration for potassium plus, then we have a different number of core electrons. These right here are our core electrons. That's going to be a total of 10. So we have 19 minus 10, which gives us a value of 9 for the effective nuclear charge here. All right, remember, when it was just potassium and we had this 4s shell right here, our core electrons was everything below the n equals 4 quantum number. But for potassium plus, since we lost that electron, our core electrons are different. And that resulted in a different effective nuclear charge. And from this analysis, we can see that the effective nuclear charge is highest for the potassium ion. And so the correct answer for 13 is D. Now we can move on to problem 14. Problem 14 says, why do halogens often form ionic bonds with alkaline earth metals? Now, halogens are found in group 17 of the periodic table, and these elements, they have high electronegativity and electron affinity, meaning that they have a strong tendency to gain an electron to achieve a stable noble gas configuration. Alkaline earth metals, these are found in group 2 of the periodic table, and these elements, they have low ionization energies, meaning that they easily lose their 2 valence electrons to achieve a stable noble gas configuration. So then when halogens and alkaline earth metals react, the alkaline earth metals, they lose their valence electrons, and the halogens gain these electrons, forming ionic bonds. And this transfer of electrons allows both types of elements to achieve full outer shells, which are energetically favorable. So keeping that in mind, let's analyze each of these options and figure out which one is correct. Option A says the alkaline earth metals have much higher electron affinities than the halogens. This is incorrect. Halogens have higher electron affinities than alkaline earth metals. Electron affinity, again, is the tendency of an atom to attract and hold an extra electron, and halogens have a high electron affinity because they're just 1 electron short of a full valence shell. So A is not the correct answer. B says by sharing electrons equally, the alkaline earth metals and halogens both form full octets. Now, this is incorrect. They form ionic bonds, and ionic bonds involve the transfer of electrons, not the sharing of electrons. That's covalent bonds. Covalent bonds involve the equal sharing of electrons, which is not going to be the case here between a metal and a non-metal. So B is also not correct. Then answer choice C says within the same row, the halogens have smaller atomic radii than the alkaline earth metals. Now, this is true that within the same period, halogens have smaller atomic radii than alkaline earth metals, but the statement really doesn't explain why they form ionic bonds. The formation of ionic bonds is more directly related to their tendencies to lose and gain electrons. Then if we look at answer choice D, it says the halogens have much higher electron affinities than the alkaline earth metals, and this is correct. Halogens have high electron affinities, meaning they readily gain electrons, while alkaline earth metals, they have low ionization energies, meaning they readily lose electrons. And this combination leads to the formation of ionic bonds. So the correct answer for problem 14 is therefore going to be answer choice D. And now we can move into our last and final problem that says, what is the highest energy orbital of elements with valence electrons in the n equals 3 shell? If n equals 3, then L can be anywhere from 0 to n minus 1 in terms of values. So when n equals 3, L can be 0, 1, and 2. L equals 1, this refers to the s orbital. L equals 1, this refers to the p orbital. And L equals 2 refers to the d orbital. And the highest energy orbital of these options is going to be the d orbital. Therefore, the correct answer for 15 is going to be C. And with that, we've completed this practice problem set. I really hope that this was helpful. Let me know if you have any questions, comments, concerns down below, or feel free to email me. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.